Hello and welcome in this third part of the series of webinars named Are you in the mood for better simulation educational? Today we'll see how to build an executable model to complete a system model to run a simulation in closed loop mode. The agenda for this part number 3 is about how to prepare the environment model, so we will talk again about how key is to differentiate the system model from the other models. We will see some helpful features from Cameo Systems Modeler, which is using an interpreted mode technology, as we saw in part 1 2 months ago. Later on, we will have from a practical example some snapshots to illustrate this simulation. Just a few words about me, as I hope now that you know me. I'm involved in modeling tools for several decades now, mainly focusing in embedded systems domains, avionics, transportation, automotive, and so forth. My current position is as an independent consultant, delivering trainings and consulting for system engineering purpose, using my strong experience promoting tools such as StateMate, Rhapsody, Artisan Studio, and so on. MBSE is my core skill with a large expertise in SysML. To summarize the key messages we addressed in part 1 and 2, first, simulation can help to achieve requirements validation. Then, we must isolate system model elements from other simulation and tool-related items. For instance, anything related to the environment can appear in the global repository model, but they should be clearly separated. Most diagrams can be executed, but the focus for this webinar will be on state machines for describing block behavior. So the goal for today is to address how to build an environment model that will interact with our system model in order to form a global executable model, including on top of our system model the related inputs and outputs. We will use a simulation profile for achieving this goal. The key message here I want to deliver, this is a reminder, always separate the system model elements from other kinds of model. Environment, scenario execution, testing, and pretty soon we also see how to build GUI for managing simulation an easier way. So our first task here, when closing the loop, will be to create specific storage locations. In SysML we call them packages, where to store and specifying elements and the diagrams collecting them. Basically, closing the loop means we will supply to the system models input values coming from the external world, those values being requested to observe the expected behavior. This can be sensors or data coming from computers, users, and so on. Also, the outputs produced by our system model might be used for reacting to a request, for instance. This is achieved in previous steps, such as interactive local simulation, as described last month with the second webinar, by setting values by hand in the simulation pane. But complex systems might have too many values to change. The sequence might be difficult to enter. In other words, we'd like to automate as much as possible the values set up. A similar approach will be used for testing, when applying specific test cases to our model to demonstrate requirements are fulfilled. Most of the time, this is useful to set the system into a specific state. In other words, put the system model in the right precondition for executing a scenario. One advice I will give here is to avoid as much as possible using concurrent states in the system model. To me, they are typically indicating a lack of functional analysis and a poor architecture specification, except for very seldom situations. And also, except in the environment model, as this is the area we don't need to communicate models for understanding the system under definition. The environment model role is, or should be, restricted to stimulate inputs to mimic signals, information, physical values coming from sensors and so on, which are needed for the system behavior. So readability and architecture for this kind of model is not that key actually. We want to show here how to connect the system model to the environment model. Our system model being a central locking feature for a car. We saw this example in the previous webinar last month. This is most probably a feature you already used. Lock or unlock your car using a remote control, often linked to the ignition key. We oversimplify the system model with only one block and one value with Boolean type, representing the status of the latches. Engaged, the car is sealed, or disengaged, the car is accessible. Obviously, the architecture behind would be more complex in real life, but anyway, we expect in our system model to get a top block representing the system as a black box. We have here another top block which represents the surrounding part of our system. Inputs, outputs, sensors, actuators, and some other data intelligence means. Included in the context are the bolts, the flashes, and internal light for helping the traveler to get some feedback from our system. We specified the central locking behavior using a state machine with 4 main states, 2 obvious ones where the car is either locked or unlocked, and in between going from the 2 main states, intermediate states, useful for specifying expected behavior. One can see the relationship between our environment block and the system, meaning our system. One can see the relationship between our environment block and the system, meaning our system model is actually part of the environment, which makes sense, isn't it? We will also use for describing the environment behavior a state machine, also with 4 states, but more details to get quite a realistic simulation results. The 2 models will operate hand in hand. They have to be tied together. Please note the role name of the latch management part association, remote, that will be used in the next slides. We will describe more precisely the environment state machine by zooming its graphical reports. This state machine is representing needed sensors value and simulating actuators dynamics, reaction time, for instance. In a car, there is a number of electronics control units, ECUs. We assume the one managing the central locking feature will communicate with others through some network data exchange, for example, to eliminate the car when unlocking, and using the indicators to acknowledge lock or unlock orders. Also, we may want to introduce some errors or bad values to check our system model against unwanted scenarios. A few words about Cameo API, which is based on ALH, standing for Action Language Helper, which is based on Java syntax. The main available features for this API are getting or specifying a structural feature value, calling a specific behavior, a specific operation, creating a runtime object, a signal instance, sending a signal instance to a specific target object, evaluating an expression, checking the state of an object, adding or removing a value to an object, accessing current simulation time and simulation time units, managing global variable, and last, checking a visited state. For our example, we want the sensor value indicating the car is locked to be updated. The line located in the green comment here is the one to use for achieving this. Remote is the role name we just mentioned before, to be used as the path. Latch is the value name contained in the block. And true is the value content, which type is a Boolean. So when entering into the no flash state, this API script will be executed. We saw that system models should only include requirements related elements. So please, no pollution inside, but we can put anything else in the environment model. As this is out of the scope of the specification, we don't have any issue using so specific tricks there. But this is also requested to close the loop. To use the environment model connecting to the system model, as we saw in the previous slide, we have to use a simulation profile in Cameo Systems Modeler. In a simulation profile, we can assign which part of the model we want to execute. That means the top block used. All parts and references linked to it will be executed as well. We also set some other parameters, trace for execution, various formats are available, animation kind, clock setup, GUI connected, and so on. Using simulation profile is then easy. You just need to select the one to use and run simulation from the toolbar here and click on this part. This will lead to get the simulation management panel in which you can change various parameters, generate events, change values, put breakpoints, and so on. As you can see, both environment and system state machines are executed and you have access to all variables as a whole. In real life, we may have more parts and references reflecting the system architecture. As we saw in previous webinars, you can also generate some events here and set up some specific values in the simulation pad. So this is how the two state machines will be interconnected by the simulation by launching the simulation profile actually. And as we saw here in the environment model, when entering this state, which is the current state, we will execute this script as we just described before, meaning that when the latch value is set to true, which is the role of this keyword when, and there is a comparison with the Boolean with its value, we will execute the transition from locking to sealed. As a conclusion, we have seen that interactive simulation can help, meaning each time we have modeled a state machine on activity, we can validate them by running simulation. But of course, then we will have to complete our model. It's more difficult to use it in an iterative way, as this is painful to initialize all inputs, change values, trigger events from the external world. In other words, that means we need to close the loop to bring our system model next to an environment model, where input will be connected to output and vice versa. So back to our latch Boolean value, this will be managed by our environment model, which will be in charge of mimicking the external world. Automation is the way to go for focusing on scenarios for validation of requirements. Next month, we will add to the simulation profile a GUI, and we won't use too much a simulation control panel anymore, but indeed use the buttons, sliders, and other user inputs, graphic elements to control system execution, and then getting results in a more convenient way, indicators flashing, internal light on and off, and so on. So thank you for attending again this webinars. Stay tuned for the webinar number 4 next month, just before Christmas time. We will talk about how to add a GUI and the simulation profile, one or several actually, making our life easier for validating our requirements. You can still reach me using my email, olivier.cas.consulting@gmail.com. Next webinar, this should be roughly time for my book to be available, so stay tuned.